just a reminder, this is being recorded, so please either drop off and watch on the live YouTube stream, or know that you're being recorded. I don't think the text channels gets recorded, so if you're except as a text channel in Discord, so maybe that might be a better place in the discussion, CET466 discussion area. Okay. Here we are again. Again, there's the reminder, just in case you forget, or I forget. It's more for me than you. I sometimes forget to turn the recording on, and I'd rather have stuff recorded. Okay, so we've gone through 2 weeks already, and we've done 2 labs. First one was getting either installation or access to Quartus and Multisim. The second one last week was to look at putting together a half adder using Multisim. We're going to do the same thing this week in the lab, but we're going to use Quartus to generate it. And I haven't ever used Quartus for schematic entry, so we might try and play with schematic entry. I do want you to do it using Vhdl, which is, I'm going to introduce that this morning. But schematic entry may be a lower bar to jump, because if you've done it using Multisim, then you've done schematic entry for the half adder already, and so you can do something very, very similar in Quartus. So we'll see how that goes. Like I said, I haven't done it, so it might be an education for me as well as for you to see how it's done during the lab. Okay, there we go. That's the next page. So what happened, we never did get to that clock generating circuit. I do want to talk briefly about that. Please have a look at that when we get to it. I think it's first up in the list. I do want to talk a little bit about devices and stuff. Please mute. Feel free to unmute and ask questions. That's perfectly okay at any time. But if you're listening, please keep yourself on mute until you need to ask a question. And I'm having trouble. My phone has decided to. I'm watching the text channel, the discussion channel on my phone, and it's decided to disconnect its power. So I'm hoping it's going to last this morning. Okay, let's go to the next one. So one thing I want you to get out of this course is some idea about how the various pieces hang together. And what we're trying to do with digital logic, I think, can everybody mute, please? Let me just check, and I will go through and mute everybody. That may mean that you can't unmute, but I'm just getting a lot of noise. I don't think it's me.
On your end, it will stay unmute. It will stay muted forever.
Yes, that's the problem, and I don't think that's necessarily what I want to do. So can everybody just mute so we don't get the... Okay, so we're talking digital logic, right? Zeros and ones. And the trouble is we've got to represent those zeros and ones using a voltage, right? And the usual way to do it is you put a threshold, and anything above the threshold is a 1, and anything below the threshold is a 0. And the trouble with that is if you get a voltage that goes up and down, right, around that threshold, all of a sudden you get chatter, right? You get the logic 1, logic 0, logic 1, logic 0. When really, so remember, we really don't have our signals going abruptly, right? We have the change happening gradually. And if that change happens gradually with a bit of noise, then as that change in voltage goes through the threshold, determining the difference between a 0 and a 1, you get chatter, right? You get the output going, or the assumed value of that voltage going between 0 and 1. And there's this idea of a Schmitt trigger, which is well, the aim is that instead of having a single threshold, there's two thresholds. There's a positive going threshold and a negative going threshold, right? And the aim is to right, so you've got two thresholds, and you only go to the positive value, to the logic 1, once you go through that top threshold, and you only go to the logic 0 when you go through that bottom threshold. And another way to think about this is the idea, it's called hysteresis, right? Hysteresis shows up in a lot of stuff, particularly when you're trying to that was odd. Reduce noise, or the effects of noise. And where did we go? I want that one, I think. Yeah. So this is what's happening, right? If you've got a single threshold, like in the middle of the middle diagram here, right, and you've got your noisy signal transitioning from a 0 to a 1, this is the green is the 0 level, and the red is the 1 level, but we've only got a single threshold. So on the rise, you get chatter between the 0 and the 1 because of that tiny bit of noise around the threshold. And then on the downside, you also get that chatter between the 0 and 1 because you're oscillating around that single threshold. But what a Schmitt trigger does is, and it's drawn with this hysteresis loop inside the NOT gate, right? This is a NOT gate. But with this hysteresis loop, you can it's got this double threshold to try and stop what we've been talking about happening. Okay, so that's one thing I thought we should talk about. Sometimes you see those these devices with the hysteresis loop in there, and this is what it's doing. It's a good thing usually for noise immunity. So that's the first piece I wanted to talk about. The next piece I wanted to talk about is I wanted to get towards circuits that generate clocks. Remember, we talked about synchronous versus asynchronous logic circuits, and a synchronous circuit has to have a basic clock that all of the inputs and outputs change on Whereas an asynchronous circuit, all of the outputs change immediately when an input changes. Okay, so that's the difference. The synchronous circuit, the outputs change on either a positive going clock edge or a negative going clock edge, one or the other, not both. And an asynchronous, it changes immediately, the inputs change. So sometimes what you want to do with an input that changes state is you want to capture that change of state. So an input changes from a 0 to a 1 and then immediately goes back to a 0. But sometimes you want to change state and keep state, right? So you want to change from a 0 to 1 and then you want the output to stay at a 1. And the way you change that input that goes from 0 to 1 back to 0 into something that stays at 1 is through what's called a one-shot. And sometimes it's called a monostable multivibrator, right? And they're called a monostable because they have only one stable state. And the idea is that they're sitting in their one stable state, and then the input comes along and it bumps it into the other stable state. I'm wondering where the music's coming from now. Has anybody got music playing? Yeah, so everybody please mute. Just to stop anything else coming in. Ray, I think you're unmuted. Would you mind muting? Okay. So here's an example of a one-shot. And the thing with a one-shot is there's another option you have with it, which is to re-trigger, right? Some one-shots, as soon as they change state, they won't go back to the previous state. They'll stay, if they transition from a 0 to a 1, they stay at a 1. If it's re-triggerable, then you can have it go back to the previous state. Right, so here's an example. We've got a trigger input. That's the top line here. Right, and what this one's doing actually is we've set up, instead of following the input immediately, we've set it up so by selecting R and C, we've set it up to output a pulse of a given width. Right, so as soon as you get the trigger, you output that pulse, and if the trigger input is shorter than the pulse, it doesn't matter. The pulse that comes out is TP in this case. If the pulse that goes in is longer than TP, it doesn't matter. The pulse that comes out is TP long. Now, I didn't explain what re-triggering is quite clearly enough. Right, so you always output a pulse of at least duration, in this case TP. What retriggering does is, if during TP, the initial output of the pulse, you get another transition, another trigger, in the non-retriggerable operation, it doesn't matter. The pulse output will be TP long. If it's retriggerable, then what you'll find is the pulse is going to stay high for TP last time past the last trigger. All right, so in this instance, here's the trigger, there's the TP pulse, then we go down, here's another trigger. There is a second trigger at point D here, and if this were retriggerable, that would restart the count, the TP count, so that the pulse would continue for another TP. This is in the non-retriggerable mode, so the one shot just ignores D, and it also ignores F. Okay, so that's what's happening there. And what's this one? So positive going transitions at points D and F have no effect, and we just talked about that. And okay, so again, I talked about the output pulse is doesn't depend on what's happening on the input. The output pulse is always the same. Oh, I don't know what's happening. I think I took this from an animated it's like a ghost in the machine. Yeah, see, it's just maybe if I don't use the mouse. No, I do not know what's happening there. Let me see if I can turn off. I don't know why it's doing that. Let's just do it this way. It's not ideal, but it will stop. And that's just the... Okay, so here's a comparison between having things retriggerable versus having it non-retriggerable. Right? Here's the pulse coming in, and here's our TP duration output pulse. This is the non-retriggerable, so we've got another pulse coming in immediately beforehand, or sorry, during the output pulse high mode, but it doesn't change the duration of the pulse. What happens in retriggerable mode though is, as soon as that positive going transition comes in, we reset the count on the output pulse, right? So the output pulse, this duration here from the dashed line to the end to point 8 is is TP. That's the output pulse duration that we've set. Okay, let's see if we can... get stuff happening without animations. Okay, so two things we've talked about so far. One of them is Schmitt triggers, one of them is monostables or one-shots. Next thing I want to talk about are clock generating circuits. And these are all examples of multivibrators, right? That's why I'm talking about them all at the same time. And this third type it's a multivibrator, but now it doesn't have a stable state, right? And can be called an astable or free running multivibrator. And the nice thing about these is that it lets us generate clock signals, right? We need to generate clock signals if we want to have synchronous logic circuits. So one way to generate a clock is to use an inverter, a Schmitt Trigger inverter, and put an RC network around it. And depending on the value of R and the value of C, we get an appropriate frequency of the clock coming out. Okay, so let me see if we can figure out what's happening. Right, remember this is an inverter, so if we've got a logic 0 here, we have a logic 1 here. If we have a logic 1 here, then that's going to pull up this input, right? Once this capacitor has charged, then it's effectively an open circuit between ground. Once that's effectively an open circuit between ground, that means there's no current flowing through R, so the voltage here has to equal the voltage here. Once the voltage here is a 1, that means the voltage on the output of the inverter has to go back to a 0. Right? Voltage on the output goes back to a 0. So now we're left with a charged capacitor. So now we're going to discharge the capacitor through the resistor. Once that capacitor is discharged, again, the capacitor is going to look like an open circuit. So now we've got a logic 0, so because the inverter is coming through, we have to get a logic 1 on the output, and we start all over again. Right? So it's a very simple feedback loop that causes the output of the Schmitt trigger to oscillate between a logic 0 and a logic 1. However, that can be a little hard to so the main problem here is you notice the approximately equal to. That can be a little hard to get right because it's going to vary a little bit per device. There is a nice little integrated circuit called a 555 timer, and it's nice because it lets you turn the analog waveforms directly into TTL compatible outputs, and for certain values of resistor and capacitor you can generate pretty accurate clocks. It's not as accurate as using a crystal, and I'm not going to talk about using crystals. Most of your computers are probably running a clock with a crystal rather than a 554. Definitely running a clock with a crystal. crystals tend to work at higher frequencies than 555s. So this is what the yellow, and it's doing it again. Don't you hate that? Okay, so it's probably something to do with my mouse, I think. So the yellow box where it says, the top yellow box is the insides of a 555, right? So we've got on the output, you can see we've got an SR flip-flop. On the inputs to the SR flip-flop, we've got 2 voltage comparators, right? Does anybody know what a voltage comparator is? Let me try bingo. Amalgamoid. I think that's Evo, is it? Is that right? Do you know what a voltage comparator does? No? Well, let's try somebody else. I'll try bingo again. Oh, we've gone through the list, so if I do it again, you might get re-asked. Wait! Okay, Evo. It tagged me the first time, and I know the answer. So what's the voltage comparator, Evo? Well, you can type away. It's okay to type the answer. You don't have to speak. It's perfectly okay to type the answer. I might read out your answer if that's okay, just so that it makes it into the recording. Yeah, so it's a bit hard to see. Let me see if I can make the picture a bit bigger. Right, so there's it's a bit bigger, and you can see those voltage comparators are they look like an op-amp, right? An operational amplifier. They've got 2 inputs. They've got a plus input and a minus input, and that is exactly the way you would draw an op-amp. What a voltage comparator does that's different from an op-amp is op-amps sometimes try to be what's called linear, right? And voltage comparators make 0 claims about that. All they do is, if the plus input is bigger than the minus input, then the output goes to the positive supply rail, and if the negative input is bigger than the positive input, the output goes to the negative supply rail. Okay, so it's just a way of saying, is this input voltage bigger or smaller than that input voltage? That's why it's called a comparator. And you can see the way it's set up inside the chip. There's effectively 2 thresholds. There's a 1/3 VCC threshold on the bottom voltage comparator, and there's a 2/3 VCC threshold on the top voltage comparator. And you can see there's just 3 resistors there forming a voltage divider to be able to do that. Okay, now there's an external capacitor that sometimes you want to put on there, and that external capacitor on pin 5 lets you keep the voltage, the threshold voltages constant. And what else do I want to see here? That's about it. You do need external components, primarily for that control voltage, but also for the setting the frequency. Right. The nice thing about a 555, as you can see down the bottom there, is you can actually set the duty cycle of the clock output. By duty cycle, that just means the ratio between how long the output is low versus how long the output is high. And as you might be able to read there, the low time, TL, is 0.94 RB times C, and the high time is 0.94 times RA times C, where C is here, RB is here, and RA is here. And actually, they might be. Sorry, these numbers, the pink, in the darker pink, that's if you've got a back-to-back diodes in the place of RB instead of just having RA and RB. If you've just got RA and RB, then TL is 0.693 RBC and T high is 0.693 RA plus RB times C. And the nice thing about these chips is they're very cheap. They've been around for a long time, and they work pretty well. I have a particular affinity for these because, and I'm not going to go through all the slides about this. I just wanted to go through this one, but I have a particular affinity for these because when I was doing an internship, I think I was a junior, I think. This is one of the pieces of information that you get in the data sheet, right? It talks about the frequency of oscillation based on C1, R1, and R2. And I was working for an electrical a power company. They were the distribution company. They didn't generate the power. They just distributed it. And they used between all the substations that they managed, they used modems to communicate with the equipment in the substations if they didn't visit the substations directly. And they'd actually, this was a long time ago, so it was hard to get decent modems. So they designed their own, and they just had 2 batches of 16 modems, so a total of 32 modems generated. And the first batch all worked perfectly. Of the second batch, only 2 of the modems worked. And they didn't know why, and they didn't have time to figure it out, so they said to the intern, hey, figure it out. So I sat down and, for a start, I never knew how a modem worked before that, so I had to figure out what the circuit was doing. And what happened was between the first lot of 18, the first batch of 16 and 2 of the new batch, and the second lot of 14, they changed 555 timer manufacturers. I've forgotten who it was. Might have been going from National Semiconductor to might have been Schlumberger was the... Anyway, there were two manufacturers who made them. And it turned out that there was a difference, even though they were still 555 devices, there was a difference between the two manufacturers in this graph. And in this graph, for the original ones, they'd chosen the right values of R1 and R2 and C. But for the second manufacturer, for whatever reason, their manufacturing process was different. They had a completely different set of values, and those equations for figuring out the T high and T low. And all I had to do was replace one of the resistors, and replacing one of the resistors on all 14 of them fixed the problem. But it took me a couple of weeks to get up to speed with how the modem worked, because I'd never seen a modem before. But yeah, it was sort of interesting. Anyway, there are a lot of other slides about the 555 here. I'm not going to go through them. I suggest you have a read through them just to see. Particularly the next one here is about how you can add a diode to help things a bit. But the prime thing is this usage here, where you've got the control capacitor to keep those thresholds set. You've got R and C, or you've got the two resistors, and you've got the capacitor. That's the prime way of using it with outside devices. So if we were in the lab, I would one of the labs I would give you is to put one of these together. I may actually put together a bonus lab to run in Multisim to get one of these working. I think that might be, it's actually not a bad idea. I'm just going to go grab my notebook. I left it in my backpack. I realise we're all electronic these days, but for whatever reason, I remember stuff better if I write it down than if I type it. So I'm going to write it down. And this is for CET466 2020. And bonus lab for a 555. Like I said, normally I'd get you to actually put it together in the lab, but I didn't think about making a multi-sim lab for it, so we might do that. Okay, all very important stuff in terms of getting a clock, right? Or if it's a Schmitt, just the Schmitt Trigger input, it's conditioning the input. I don't know whether I've got any here. That might take a bit much to. So another reason you might use a Schmitt Trigger is when you've got a mechanical switch going from one piece to another. Let me just turn that off, and I'll turn me into big me, if I can figure out where Streamlabs got to. There it is. There we go. So if you've got a mechanical switch, normally a mechanical switch is something that goes from physically transitions from one place to the other. And the trouble with a mechanical switch is that it doesn't immediately break contact. It chatters a bit, and it doesn't immediately make contact. It chatters a bit. And you can imagine that causes chatter on the on the signals that we're measuring, right? That we're looking at, the digital signals. And having that problem is called the switch debounce problem. And that problem is inherent in trying to convert from a real world signal into something that a computer can deal with. So have a look at that. Okay. So last time we looked at the two different sorts of machines, a Moore machine and a Mealy machine, right? And the prime difference is where the outputs are generated from. The Mealy machine, the outputs for the device are generated from the combinational logic. And the Moore machine, the outputs are just kept in memory. Right, so and the idea is, let me just fire this up. Oh, I forgot to sign into the right version of OneNote. Let me just sign in there. Right, so the idea is that you can it may be easier to just design a counter and determine the output of the counter based on the counter number 0, 1, 2, 3, 4, 5. It may be easier to generate the output from that counter than it is to do something other than just going 0, 1, 2, 3, 4, 5. Okay, we want that one. Sorry about this. I should have, I usually prep a bit better. So let's add another page, and this is Lecture 03, 2020, 09, 12. Okay, so as I was saying, let's just think about let's think about a really simple counter, a 2-bit counter. Right? We go from 0, 0 to 0, 1 to 1, 0 to 1, 1 back to 0, 0. Right? So this is 0, 1, 2, 3. But suppose we wanted the sequence the grey code sequence, right? 0, 0, 0, 1, 1, 1, 1, 0. Suppose we wanted that sequence. Well, one way to do that would be to have the state machine do that, right? 0, 0, 0, 1, 1, 1, 1, 0, So that would be one way to do it. And in this case, this way of doing it would be the Moore machine, right? Because we're just reading off the state information directly. We're just reading to get the outputs. We're just reading state or memory to get the outputs. Right? The other way to do it, the Mealy way, would be to just do the simple counter. So this is a simple counter, and this is the grey code counter. So the Mealy way of doing it would just be to do a simple counter and then change the outputs, right? Or put combinational logic in place to generate the outputs. So do a simple counter and put logic in place to generate required output. Okay, and how do we do that? Well, let's see if we can for some reason it's decided to not let me make it go bigger. There we go, that's a bit better. Not quite sure why it changed pictures, but I wanted some space down the bottom. So what we do here is we take our state from our simple counter, right? We go 0, 0, 0, 1, 1, 0, 1, 1, and the outputs we decide are 0, 0, 0, 1, 1, 1, and then 1, 0. Okay? And now we just have a truth table. And as you should be able to see pretty directly, this output here is just, if we call this input A and input B, this is just A, right? And you should be able to see, well, this one way to look at this one is it's going to be A bar B or A B bar, right? But you should recognize that as A exclusive OR B, right? The output, this second output, is only high if only one of A or B is high, right? And that's the exclusive OR output. And excuse me, that way of doing it may end up being simpler than the logic you need to make the Moore version, right? The Mealy version may be simpler than, because with Mealy, the only thing you need to generate a standard counter, a modulo, in this case modulo 4 counter, is flip-flops. We don't need any external logic because we can generate Q and Q bar easily. Okay. And all that's in the next couple of slides is a slightly more complicated version of that. I thought it might be easier to come to grips with a smaller version, just a modulo 4 counter. Okay, and obviously A is really easy to get, and okay, we do need an exclusive OR gate for the other output, but that is also pretty simple to get an exclusive OR output. I didn't post a complete set of the slides. Yeah, so part of the, I think I did, but let me just check. I have a problem with Discord in that it only allows me to upload 8 megabytes worth of file at once, so I had to split the Discord versions into 3 separate files. There's part 1, part 1b, and part 2. And I think I did upload the, let me just check, maybe I didn't. I thought I uploaded the complete thing into Blackboard. But let me just check, like I said, 466. Oh, maybe it wasn't the right. Yeah, there should be. I think it should. All of the slides for should be there in Blackboard, but sorry, in Discord. But like I said, I had to split them up into 3 separate files, and there are actually in Discord there are 4 separate slide decks. Oh, are they the same? Are they? Oops, sorry about that. I thought I got them. You're right, part 1b. Sorry about that. Let me see if I can fix that. I won't do it now, but I'll. If you look up on Blackboard, the full slide deck is there. But after this lecture, I'll fix part 1b. In fact, before I do anything more, I will delete part 1b from what's there at the moment, and I'll upload part 1b. Thank you for pointing that out. Apologies for getting that wrong. Okay. Okay, what have I got? There we go. Let me just check the... Yeah, that's all right. Okay. Let's go on to the next bit. So the next bit, I think the part 2, is that right? Yeah, so I'm next going to move on to the part 2, which looks like it did upload appropriately. Anybody got any, before I go on, anybody got any questions about what I just talked about? Right, so far we've done 2 things, looked at various forms of multivibrator, and I did a quick reprise of the difference between a Mealy machine and a Moore machine. So let's do this. So finally, after 2 and a bit lectures, I'm actually going to get to the nub of the problem, right? the whole reason I'm doing this course is VHDL, right? And it's worthwhile. I think it's worthwhile taking it at least the first 4 or 5 lectures relatively slowly. So VHDL is a hardware description language, HDL. There are 2 prime hardware description languages. There's VHDL, which stands for Very High Speed Integrated Circuit Hardware Description Language. I don't know why they just decided to go with V for Very High Speed Integrated Circuit, but they did. And the other language is one called Verilog. And I haven't quite figured out the exact numbers, but it's roughly 50-50 between people who use Verilog and people who use VHDL. This course has primarily in the past been taught with VHDL, so I decided to stick with that. One of the former students of the CET program has been trying to convince me to switch to Verilog. I may very well switch to Verilog next time I teach this, because there's some really nice open source tools available for Verilog. Unfortunately, I haven't been able to get them to program our boards, either the ones in the lab or the ones I have acquired since. But VHDL is pretty good. And the generation of VHDL its intent was for documentation. It wasn't originally intended to actually be able to synthesize stuff. But that's what it does now, right? So there's lots of places we can do design. Right, at the top level, when we're designing a computer system, we write down the specifications, right? When we're writing a program, we talk about algorithms, right, that run on a CPU and deal with I/O and memory of one form or another, RAM or ROM. Down at the register level, right? We might talk about state transitions, and that's what we were doing earlier today and in previous lectures. Diving in a little bit more, we might talk about Boolean algebra at the gate level. Diving even further down, those gates, even though we think about zeros and ones, are actually being done using voltages. So we've got to think about Kirchhoff's voltage law and Kirchhoff's current law and the differential equations around how resistors, capacitors and inductors work. And the circuit diagram there looks like it's got a FET, a field effect transistor, and a capacitor, and so we've got to think about how transistors work. And then all the way down to the silicon, where we might actually have to deal with fundamental physics about how things work. Right? And the stuff we're interested in for VHDL is to try and deal with the top 4. And most of the stuff we're going to be doing is in the middle 2, the gate and the register piece. We might also deal with the chip level. So, what does VHDL do? Well, one way to do VHDL is the same way we work with multisim, and that's the schematic way, right? And the way the tools that use VHDL, or that allow you to use VHDL work, they split the way to do things between a behavioral approach, and a structural approach. The schematic approach is the structural approach, right? You draw the structure of the circuit. Okay, we've talked about the half adder, and in fact this is even less than a half adder because it doesn't have the carry output. The other way of doing it, not the structural, the behavioral approach, says, okay, we've got this box and it's called adder and it's got two inputs and it's got an output, right? And we want to decide, we want to make sure that the right thing, if something happens on the input, that the right thing happens on the output. Right? And that right thing is the behavior of the thing. So there's two pieces. The first piece is what happens around the periphery, the interface. How many inputs has it got? How many outputs has it got? And then the next piece is the behavior. Well, how do you move from those inputs to those outputs? And Vhdl splits those two things between the architecture and the entity, and we'll see how that happens. If you've got multiple boxes, then you've sort of got two different scopes, if you like. In each adder, you've got the two inputs and the output. But then if you've got multiple devices in the same design, then you've got those inputs and outputs in each adder, but then you've got the connectivity between each of the different devices. And that's the way that's done is between internal signals and external signals. So the standard way of writing a particular device is to define the entity. This is a way to name a device and to define what the ports, the inputs and outputs are for the device. And you write that in a .vhd, the file name extension for Vhdl files is .vhd, and each Vhdl file should have at least two pieces, the entity part and the architecture part. The entity defines the boundary, what goes in and what goes out, and the architecture defines the behavior, right, or the structure, or how it all hangs together. And yeah, that's about it. So there's a few things. Vhdl is a programming language, right? It allows you to program bits and the relationships between them. But the key piece is that it allows you to turn that program into hardware. It's not a program running on the hardware like you would if you were writing in Java or C or C#. It is actually reconfiguring the hardware in order to do this. Okay, so I'm going to back out of this. This is page 45, and I'm going to, before I go on, I'm going to switch over to some notes that a former colleague of mine, Professor Jasmine Banks, gave to me. And these are from the Queensland University of Technology, where Jasmine works. And they, let me just go to full screen with this. I wanted to talk a little bit about the how we get to VHDL, right? And it's all about how the technology works. So this is the standard sort of graph that you get with just about any technology. You get the introduction, you get the growth, you get the maturity, and then you get the decline. And you can see over here, I talked about resistor transistor logic previously. There's also diode transistor logic, and then a lot of these others. The standard devices we've been using have been 74LS or 74F devices. These are very, very close to being out of scope as far as any sensible design is concerned. They may be, pretty cheap, and that might be a good reason to use them as a hobbyist, but in general there's lots of other devices around. Okay. I've been talking for a bit over an hour, so I think it's about time for a break. Before I go to break, let's just make it a 5-minute timer. Does anybody have any questions about what I've done so far and where we're heading? No? If not, then I'll set the timer up, and I will figure out where Streamlabs got to. There we go. I'll mute myself and I will take off my webcam. And I'll see you in about 5 minutes. Okay, and we're back, I hope. So let's just go back to our full screen. I'm not going to talk through all of these. I suggest you have a flip through the slides that Jasmine put together, because I think they're kind of interesting. Right, this is a little bit working through some of the technology, right? So most of the devices that you've worked with in 363 in the lab are TTL, and they operate between 0 volts and plus 5 volts. Most newer devices are based on the Cmos technology, right? And we, I think we came up with that it's complementary metal oxide silicon or semiconductor as the what the acronym stands for. And one of the nice things about Cmos devices is that they have different supply voltages: 5 volts, 3.35, 3.3 volts, 2.5 volts, or 1.8 volts. The reason that's important is because it lets you run lower powered devices, right? Remember from 236 that P equals IV, which means P equals V squared on R if you apply Ohm's law. So one way to think about power dissipation is it's proportional to V squared, the voltage squared. So 5 squared is going to get you 25, is going to be significantly bigger than 1.8 squared. Okay, maybe the R is different, but the idea is that there's the potential for a much lower power dissipation going to CMOS over TTL, and lower voltage CMOS over higher voltage CMOS. Right, and just like we talked about with the Schmitt Trigger, there's a couple of different thresholds, and there's two different things here. The left-hand version of each of these is the acceptable regions on the input, and then the right-hand of each of these pairs are the acceptable regions on the output. Right, so there's 5.5 volts, sorry, 5 volt CMOS. The acceptable output voltages are much higher than the range of acceptable input voltages. Similarly, it's not quite as different in the 3.3 volts, but there's a smaller range of acceptable output high voltages and low voltages than there is on the inputs. And TTL, it's a little different, right? You've got these quite a high band, right? 2 volts or above in terms of the inputs, or 2.4 volts and above in terms of the outputs. So those differences between what an output thinks is high and what an input thinks it's high talks about what's called the noise margin, right? And you want a big noise margin. You want your circuits to be immune, hopefully, from noise. So you want the differences, these two differences on the device to be as big as possible. Okay, so here's a another thing about power. So now we have, you can imagine, because these devices do different things, they're switching with transistors or field effect transistors inside. The current each device, each gate consumes is different depending on whether the output is high or low. Probably also different depending on the input values. Right? In this case, if we assume that the duty cycle is 50%, meaning the output is high half the time and low half the time, then we get we can just take a simple average of the two current values, and then we can figure out what the average device power dissipation is. Right, and another part of the reason why Cmos devices are good power-wise is, as it says, they have zero quiescent current. Quiescent current means if nothing else is happening, the device consumes zero current. TTL devices are different in that even if nothing else was happening, they already have a current. The quiescent current is non-zero. The bad thing with Cmos is that as you increase the frequency, the capacitance of the internal nodes and maybe external capacitors increases the current, right? I equals CD VDT, which you should have learnt in 236. Maybe physics, you might have come across it first. So power consumption for Cmos devices goes up as you start running things faster. So that's one of the problems with wanting your computer to go faster and faster. That CD VDT is going to get bigger and bigger. Because you're going to abruptly change your frequency. We're going to increase your frequency. And here's a plot of various device technologies and their power dissipation against frequency. The standard logic devices we would be using are the LS devices, and as you can see, up until about maybe just below a megahertz, so maybe, what's that, it's probably about 200 kilohertz, maybe 400, 500 kilohertz, right? That's constant. Whereas all of the CMOS technologies are much lower. This one's above a milliwatt, right? Whereas these ones are down in the microwatt range, at least in this region here. And as expected, the higher the voltage of the device, the higher the power dissipation. That V squared on R is going to get you, right? It's two fundamental laws, the way you calculate power and Ohm's law. Another thing that you've got to come to terms with logic is even though we talk about it being 0 and 1 and we don't think about timing, as soon as you start devising a real device, you have to think about timing. And a device like an AND gate here has what's called a propagation delay. And there's two different propagation delays. Sometimes if the input changes and the output goes from low to high, that there's a delay there called TPLH. And then if the output goes low from high, there's a different potential delay, TPHL. And when you're dealing with real devices, you need to look up their data sheets to figure out what the propagation delays are. Propagation delays cause all sorts of issues, and sometimes it's not clear. I'm hoping for some of the later labs that we do in Quartus that we'll be able to simulate what happens when you get. What happens is, because there's this difference in time, if a signal propagates through a device and one chain of signal goes through a different number of gates compared with another chain of signal, then not only do you get TPLH, that propagation delay from low to high, you may get 2 TPLH or 3 TPLH or 10 TPLH. If there's a way through your circuit where the two inputs of one device have very different propagation delays between input and that getting to that device, then you will get glitches. And we need to talk about later, we need to talk about how to do that. The simple fix is to equalize the delays, right? You make sure that you always get the same amount of delay. And I think, let me just check, I think I put in there into the lab, what number is that? That is page 45. I think I put in a lab. Yeah, I think we'll do a lab later on where that propagation delay has to be taken into account when you do your design. Sorry about that, I just wanted to check what else the list of labs is. Okay, so let's move on. And there's just a plot. All of these physical properties of a device are intertwined, right? There's a relationship between power dissipation and propagation delay, depending on the voltages, right? You can see here as the power goes down, so you're changing the voltages you're working at, the propagation delay goes up. And maybe that doesn't sound quite right, but you can think about it. If you've got a lower voltage, remember voltage is a driving force. So if you've got a lower driving force, the physics is going to be driven less quickly. Okay, so your propagation delay is going to go up, even if your power dissipation, even if the reason you're using the lower voltage is to reduce the power dissipation. Another physical thing that you have to take into account sometimes is gates take current in order to register their inputs. The output of gates has to supply current. If you have lots of inputs connected to a single output, it's possible that that single output cannot generate enough current to drive the inputs it's connected to. And that problem is called fan out, right? there's normally one of the things that you look up on the data sheet for a device is its fan out. And sometimes the fan out is only 2. Sometimes it's 20. And you have to be able to read that. If you exceed the fan out of a particular device that you're using, your circuit will not work properly. It's one of the reasons that you often get ghostly behavior, right? Unknown behavior in digital circuits. One of the other reasons you get unknown behavior is what we talked about before, of glitches because of different propagation delays. So have a look at that. And this is just a bit more detail about fan out and loading and how things work. I'm not going to talk about the details here. Right, this is just talking in a bit more detail about what Cmos is, complementary metal oxide semiconductor, and NMOS and PMOS transistors. Right, and you can see, if you remember your semiconductor physics, there's N-doped semiconductors and P-doped semiconductors, and it all depends on which of those types of semiconductors. And you can see the way that's drawn differently in a FET, a field effect transistor device. Right, the N channel has the source pointing in, and the P channel has the source pointing out. And again, I'm not going to go through this. You should have covered this in your introductory electronics courses. And I actually found this piece, I'm not going to go through it, I found some of these slides quite interesting because it shows you how a real NAND gate might be put together using discrete FETs, right? So you've got a nice description there. Again, I'm not going to go through them, but I think they're interesting to show. I think I talked about Cmos and electrostatic discharge before, but I think it's worthwhile repeating. The reason we don't tend to use Cmos in the lab is precisely because of this. If you just touch the pins with your finger on a Cmos device, it's possible that even if you don't notice the static discharge, that it happens and that it destroys the device. Again, harking back to my internships, I used to work for a computer manufacturer in Australia, and I worked in the warranty section, the returns section, and the returns people knew that the manufacturing side, the people who made the new systems, did not understand static protections. And they, the returns people, we had anti-static mats, we had clips that we could discharge on. It was all pretty well done. But the problem was the manufacturing people didn't, and they were shipping destroyed devices, right? And as a result of that, there was a lot of animosity between the production head and the returns head, and they just didn't see it. But the returns head was correct. The company, as they were shipping the devices, the new stuff out, were being destroyed. And this is just some more. This is more about how TTLs work. So look at the difference between, this is just a simple TTL inverter, right? And you can see it's got transistors, BJTs rather than FETs, and it's got resistors in it. Let's go back and have a look at the Cmos gates, right? Sure, there's transistors here, but I don't see any resistors. There's transistors in the NOR gate, but I don't see any resistors. Whereas the TTL device is a much more complicated because of those extra resistors, and that's why what I was saying about the quiescent current, right? The not changing current. TTL devices, they're always dissipating something because there's always some current flowing through one of those resistors. Whereas the CMOS device, as soon as those transistors switch to a particular state, cutoff or saturation, on or off, that's it. They're done. They're staying there, and we don't have that extra quiescent current. And there's a NAND gate. Ooh. So sometimes a lot of the devices we work with in the lab are 74LS devices, and LS stands for low-powered Schottky, right? And the Schottky piece of that is that those devices use Schottky transistors and Schottky diodes on the input, and you can see that here. And those Schottky devices allow for faster switching, which is the main reason to use them. Okay, the Schottky piece is the fact that you've got this little twiddle on the crossbars of the diodes and the transistors, right? That's how you indicate a Schottky device over a standard BJT or diode. Bipolar junction transistor, anyone? And I don't think I wanted to talk about that. Oh. So another thing you've got to think about in your designs is how do you deal with unused inputs, right? You still want your circuit to work, and you may have set those circuits to be unused. Well, the usual thing is you either tie the unused input up to plus 5 volts through a resistor, a pull-up resistor, or you tie it low. And I would tend to use a pull-down resistor as well, rather than tying it straight to ground. Another sort of device is what's called emitter-coupled logic. And emitter-coupled logic is higher power consumption, but much faster than standard TTL. And so that's where the emitter-coupled logic comes in. And here's an example, right? And the reason it's called emitter-coupled logic is because this is the way, right? The emitter is connected directly to the output, and there's nothing else there. If we go back here, right? Here we've got a push-pull pair as the output for this example, and let's go here, so same thing, push-pull pairs. See if we've got I don't think we've got another one. Right, but the difference with emitter coupled logic is the emitter goes straight out to the, oops, where'd it go? Yeah, the emitter goes straight out. And I don't want to talk about that. There's the CMOS technology that's used. Cross 3 separate way logic states, right, in 363 and what we talked about earlier in this course. 0, 1, and X. Right? X is I don't care. There's a fourth one that I need you to introduce you to, which is the Z state or the high impedance state. Right? And effectively what that does is shown here on the 3 diagrams. The first two, you've got the device you have is an inverter, but it's got a separate input, which is the enable input. And what happens is if the enable is, and this is an active low enable, you can see the bubble on the enable input. That means when the enable input, enable input is low, that means it's turned on. And you can see that just works exactly like you would expect an inverter to work. When the enable input is high, and remember it's active low, so high means it's off. When the enable input is high, then the output is completely disconnected from the rest of the circuit. Okay? This way of doing things is called a high impedance output or a tri-state output. Tri-state meaning the possible outputs are 0, 1 or Z. Right? Completely disconnected. This is another reason why sometimes you need to have pull up or pull down resistors in your circuits. Right? You can imagine that if the high impedance output gets connected to some other input in your circuit and the output is disabled, so we are in the Z state, the high impedance output state, then the input to the subsequent device is floating. We don't know necessarily what value of logic it's containing. So it could go up or it could go down. This is yet another way for the ghost in the machine to appear, right? Undetermined inputs result in undetermined outputs. The reason you might use a high impedance output is usually when there are lots of devices connected on the same bus, right? So there might be several devices outputting onto a bus, but you only enable one of them at a time and you have all of the other outputs disabled until that device is called upon to provide its information. And this is just, I'm not going to go through, this is just how you might do an enable on a Cmos or on TTL. Right, and this is just showing that the typical example is on data buses. Sometimes you will see on the output of a device an asterisk, like in the B diagram on the right hand side here. What that means is that this is what's called either an open collector or open drain device. The nice thing about open collector or open drain devices is that you can connect an external resistor and allow that output to drive a lot more current than a standard device. Right, so this is for the TTL example. The idea is that you would have an external pull-up resistor to allow you to supply that current. It may be that if you because these devices are put onto silicon, having a resistor that can dissipate a lot of heat is not really feasible because it takes up too much space on the silicon. So having an external resistor means you can use just a standard resistor, and that resistor can dissipate more heat when it's supplying more current. Right? And a way to think about it is that's the other piece I should have said, is you don't have to have the output of an open collector device connected to the standard logic plus 5 volts or plus 3.3 volts. You can connect that output to any voltage. So, for example, the bottom line there, you can connect it directly to a 20 volt supply that's turning a lamp on, a standard flashlight lamp. You don't have to have that output voltage being the standard plus 5 volts. And there's just more examples of that. And another thing you can do is you can effectively do an OR operation by just connecting lots of outputs of open collector devices together. Normally you can't do that. If you connect lots of outputs to the same wire, that will blow something up. With open collector, you don't have the same problem. You can connect them up, and the effective operation is an OR operation. And I think I didn't want to talk about those. Yeah, I think that was about it. So, when we get to it, I'll see if I can. Let me unplug that. So when we get to it, and let me just go to Big Me again. Right, so here's our device, and I don't know whether you can quite read. Yeah, it's not quite doing the right thing, is it? Oh, that's all right. So there's two communications connectors here. This top one is labeled AS, and this bottom one is labeled Jtag. And I thought it might be useful to talk about what Jtag means. Let me go back to Mini-Me. Right? Jtag stands for Joint Test Action Group, and its aim is to allow access into these complicated devices, microcontrollers, CPLDs, FPGAs, RAM, without having lots and lots and lots and lots of wires going in there, right? It's part of a protocol. And to get to the next page, right? So the thing is, it only looks around the boundary of the device, right? So the yellow block, the big yellow block in the top here is the logic, and then all of the connections around it have what's called a cell, a boundary scan cell there. And what you can do is you can, at any given time, you can either excuse me, you can either insert data, right, on the TDI input, I think it would be. So you can put data into each one of these blue BSC cells to have a particular input on all of the pins, and you can read out the values if they're outputs by reading out the TDO, the output side of things. And the nice thing about that is then you can get really detailed access to what's happening on the chip without having to have lots and lots of probes on there, right? Here you only need, well, with all the control signals, you only need 5 connections in order to get it to happen. Whereas you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 different cells there that you're getting access to. And it's actually much bigger than that. You can get a lot more. You still only need 5 connections in order to get access to all the pins on a device. And some devices have hundreds of pins. Okay, so we're going to be using Jtag. I think I said earlier, this device is has 2 programming. It's got the AS, which is the serial programming, and it's got the Jtag. The thing with Jtag is, as soon as you turn off the device and turn it back on again, these BSC numbers have just disappeared, right? They're no longer relevant. So Jtag programming, which we'll be doing, is ephemeral, right? If you power cycle the device, it goes away. The AS programming, the serial programming, is not ephemeral. It'll stay around. It'll get programmed into the non-volatile memory of the device, so that when you power cycle the device, it comes back the same way as it was. Okay, so I thought, I didn't go through all of those slides. I thought Jasmine's talk was kind of interesting, and I thought it was relevant. I talked through the relevant pieces, and that slide deck is in the up in Blackboard and in the materials Discord channel. So let's go back to Vhdl, and I thought maybe if I can figure out, ooh, do I have a copy? Maybe I don't have a copy. So let's have a look. So that, rather than, I will get to it soon, but let's I thought it might be worthwhile, that's a bit big. I thought it might be worthwhile just having a look at what Vhdl looks like. Right, remember I talked about the boundary, or the entity, and the behavior, the architecture. So we're going to do a lab today to try and implement our half adder, right? So the way you start out a Vhdl device is you define its entity. So here it's entity, and then the name of the entity, I've used lab 3, is, and then we usually have a port description, right? And in my example in the lab, the port description has A and B as inputs and S and C as outputs. And then this std logic just stands for standard logic, and that just means it's a Boolean value. There is a standard Vhdl type called bit, but bit gets a little tedious to use. So the IEEE have defined something a bit easier to use called std logic. And in order to access that, we need to first of all pull in the IEEE library and then use the 1164 standard logic definitions. So this std logic, if you just use that in Vhdl without calling in the library, that would generate an error because it wouldn't know what std logic is. And then in order to finish the we have to close it with an end entity and then the name of the entity that you're ending. As I said, that just defines the output, or rather the boundaries, right? The inputs and the outputs. And then we need to define how it all hangs together, the connectivity of it, and that's done in the architecture statement. And the architecture statement needs a name, and I tend to just use _arch and the entity name. You don't have to, you could just say arch and that would be okay, but I tend to want to know which architecture it is, so I say it's the lab 3 arch. And then you also have to define what it's an architecture of, and this is an architecture of the lab 3 entity. Once you've defined that, then you have access to A, B, S and C. And because I actually want you to do some work, I'm just setting the outputs to 0 in this this Vhdl, right? You're going to have to figure out how to code, how to get access to A and B and make this truth table happen. Right, and the architecture statement starts with a begin statement and ends with an end architecture statement. And again, I don't think you need to name the architecture that's being ended, but it's good practice to use the architecture name. This symbol here is an assignment. It says make this number, and it's just a logic 0, go to the S output, and again you'll want to make that you want to do something different from just making it 0 in both cases. Okay. So let's go through a little bit more of Vhdl. I tend to use underscores and mostly lowercase, except for the first letter. Doesn't matter. VHDL is case insensitive, right? It doesn't matter. It doesn't care whether it's uppercase or lowercase. You have to make sure that the names start with a letter and not a number. You have to make sure you can use an underscore in the name, but it can't be two of them, and it can't be the last character in a name. And the names you use cannot be keywords, so you can't have a variable called in or an input called in, an output called out, a variable called bit. Right, so here's the what has to happen with the declaration. First of all, you have an entity name, and then you may have other signals, right? You need to, signal names, right? Then you have the mode, whether it's an input, an output, a buffer, or in-out, and then the signal type, right? So let's just quickly go back to my VHDL and look at those entity name, signal names, and signal types. Right, so here's the signal name, A, here's the signal type, direction, and here's the signal type. Right, we've got the name, we've got the mode, which is whether it's input or output, and then we've got the signal type. You have to be very careful with types in VHDL. As it says there, it's a strongly typed language. So a bit is not the same as a std logic, even though they both represent single bit values. Types in VHDL can be extended, so we can make, if it makes sense to make our own type, we can do that. So here's a simple example, right? Entity name is, port, and then all the signals and their appropriate modes and types, and then we end entity. And so those words entity, is, port, and end are keywords. You can't use those for your own variables. If you have multiple signals with the same type, you can just define their signal names and space them with a comma, or delimit them with a comma, and then just have a single mode and signal type statement, just like I did with A and B in the example, and S and C in the example. Right? A and B and S and C all have the same signal type, but the mode is different. A and B are inputs and S and C are outputs. And you've got to make sure you have a semicolon at the end, except for the last one. And then the last one, there's no semicolon after signal type, but there needs to be a closed parenthesis semicolon to finish the port. Right, so here's an example for our adder. Entity adder is port in1, in2 of type of mode in, type bit, out of mode out, type bit, and entity adder. Okay, so now we need to go back and think about the architecture. And the architecture can be a lot more complicated because there's lots of other things we can do. We need to define the architecture name, and then we need to tell it what entity we're implementing. Then after that, there's lots of other stuff we can do. We can have types, signals, constants, functions, procedures, even components. And then at the end we end the architecture, and we have to have the architecture name we're ending and a semicolon, it looks like. So this is what it might look like. Architecture name of entity name is, and then we might have types or signals or constants. So those are things that we need to define before we use them. Sometimes you don't need to define anything, you're just using something simple. And in the lab today, there won't be anything between the architecture and the begin. We don't need to do any of this stuff. For some of the more complicated stuff we're going to do, we will need to do extra stuff. And then there's the behavior or the structure, and then we end it. Right, so here's an architecture for an AND gate. Right, we just use the keyword AND, and we say that out1 is assigned to in1 and in2. And we can do the adder, right? We can just say that the output is in1 plus in2, which is kind of nice. And this is just a reminder that it's really dangerous to mix different data types. For a start, the compiler will just throw an error. But then if you think about what happens if you try to add a string to a real value, does that make sense? And then that sometimes doesn't even make sense in a normal programming language. But now remember, we're pushing it out to silicon, and it's actually going to the hardware. So what does a string mean in hardware? What does a real value mean in hardware? So we've got to think about these things. There are lots of predefined functionality. Any of the primitive types you could think about: and, or, not, exclusive or, NAND, NOR, plus. One thing with that plus operation is it only works for integers. It doesn't work for bits as it is. We can extend it to work for bits, but it doesn't out of the box. And I suggest just about everything you do in this class will use the IEEE library. And I haven't released any notes of that, but let me just make a note to release some notes about the IEEE library, because I think that would be good. So here's some standard ones. There's the 1164 that I used in the example. There's the arithmetic, and there's signed stuff. Right, in this particular example, we don't really need the arithmetic or the signed use statement, because I don't think it uses it at all. The only thing we use is the std logic type, and that comes straight out of the 1164 library. And here's another example. Right here, they haven't used those extra libraries, so it's just the 1164 one. Okay. It's about time for another break, and I'm going to talk a little bit before we break. There are still several people who haven't submitted Lab 2. Please use the time now to do Lab 2 if you haven't done it yet. We're going to do the same thing again, and I'm going to demonstrate it. Like I said, I had intended for this particular lab to be done using programming directly. But I'm going to try and also do it using the schematic capture aspect of Quartus. Lab 3 is up in Blackboard. There are lots and lots of screenshots in there to show you what to do. One thing I am going to start doing this week is, let me just stop that and go to Big Me, wherever Big Me got to. There's Big Me, right? I'm going to need to start handing these out to people. That means I don't have enough for everyone. So what I need to do, I've already handed out 2 of them, and I need to understand that those 2 and the other 10 people that I'm going to hand them out to have access to their own Quartus installation on their local machine. Just having access to Quartus via the Citrix server, the app server, won't be good enough. So I apologize, I should have checked with the 2 people who have the device already that you will have access to a Quartus installation. The reason is you need to connect up this device to Quartus via USB, and I'm not convinced that the Citrix server will connect that up. Citrix will be able to save on your local machine, but or on your OneDrive, but it won't let you connect up USBs and stuff, which is what you need to in order to program this device. So what I'm going to do is I'll set up a query in Blackboard that okay, cool, thanks Adonica. I will set up a query in Blackboard that asks whether you have Quartus installed. And I'll select from those people who have Quartus installed, and I'll organize with them to get those devices out to you. Don't worry, those people who don't have access. What I'm going to do is I'm going to, once we start using those devices, I'm going to want you to work in pairs or threes in order to get those to get that to happen, right? So you'll still be on the hook for doing VHDL, and you should have access to Quartus to be able to compile everything and run it. But then you'll have to rely on your lab partner in order to actually run the code on the the actual device, right? These are actual devices. They have FPGAs, field programmable gate arrays on them, and we can run our VHDL code like this stuff here, wherever it's got, there it is. We can run that on the device itself. Okay, so let's go back to Mini-Me, and I'll turn off my webcam, and we'll have another. Does anybody have any questions so far? Let me,
I had one question.
Yeah, go for it.
Could you can simulate the device as like that's what we'll be doing today, right?
Right.
Essentially.
That's correct. So, well, actually, no. So I've broken down the labs into baby steps. So where we want to get to is simulating the device. All I want to do today is to be able to compile VHDL without errors. Okay? And there's 3 steps. For me, there's 3 steps. Let me just go back to Big Me, maybe. Right, for me, there's 3 steps. There's being able to compile VHDL without error. There's simulating changing the inputs and looking at the outputs in VHDL. So we're not touching any hardware, it's all still done programmatically. And then the third piece is deploying the design, the tested design. That second piece, the simulation, is all about testing to see that it does the right thing. And then the third piece is deploying the design to the hardware to make sure that that hardware, to implement the design in the hardware. Okay, does that answer the question? Is that it?
Yeah.
Yep. Okay, good. Okay, so let's, I'll turn my mini-me off. I will put up I might make it a 10-minute timer this time around. And we'll come back in about 10 minutes and I'll start doing the lab on the Citrix server, and I'll also indicate the what happened, where I want to do the simulation. I'll see if I can get that done. The reason I didn't do it so far is I need to sit down and take detailed screenshots about how to do the simulation. I haven't done that yet. Okay, I'm going to go on mute, and I'll see you back in about 9.5 minutes. Okay, let's get back to it. So I think I need to, just going to move that one over here maybe. I need to start up a Citrix connection. And just so you know, it's on this one here, engineering, science and desktop connection, and I use the heavyweight Citrix desktop, which is actually an app that runs on my local machine rather than running in the desktop. I find it a little better than just the one that runs in Chrome or your browser. Okay, so I've got that, and I am going to depart, like I said. I don't want that. Where did Quartus go? Oh, it's asking for read or write access. Yes, that's okay. Quartus, there we go. Quartus Prime, it's called, not Quartus 2. That's okay. So here we are in Quartus, and these steps are in the Lab 3 screenshots. I suggest you do New Project Wizard. I think the screenshot said do it from here, but it's available here on the home page. So here's the introduction. This is the stuff it's going to do. Right? Project name and directory, name of the top level design entity. Remember what an entity is, and you have to make sure that the thing you put in now is the same as the name you use in the entity description in the VHDL you're going to enter. Right? So let's continue. I'm going to try and put this on my Mac, and I'm just going to try and put it, if I can figure out where it got to. Here it is, Dropbox, and then I have a Peter directory, professional, CCSU, OneDrive, Logic Design, and then this one, and there's labs, and I'm going to do I'm going to call this I'm going to make it a new lab, so this is the live one. Live Lab 03. So forgive me if I make mistakes in this one, right? So that's the folder I'm going to select, and this is I'm going to call both the project and the top level design entity Lab 3. If you wanted to, you could call the top level design entity half adder, right? Half underscore adder, because that would be a better naming than Lab 3. So let's do that. So the project is Lab 3, but the entity that we're interested in is the half adder. And I'm just going to go with an empty project. I'm not going to do a template. And now, if you already had a VHDL file that you wanted to add to this project, you could add it here. But I don't yet, so I'm not going to add it here. Right, so now the device. Right, there's 3 options in the family, and our device is a Cyclone IV, and it's the E type. Right, so that's worthwhile noting. And then you'll notice that there are lots and lots of E-type devices. And I need to look up the lab because I think I put the E-type device explicit name in that list of there we go. EP4CE6 E22 C8. Right, so EP4 CE6. So I'm going to go down a bit. EP4 CE5 C5 CE. Oh, okay, that's interesting. Yeah, I'm not quite sure why it's locked down so much, but sometimes it does. One reason, even if you don't normally have to run Quartus as admin, if you're running it to program the device, so to get access to the USB connection, you may need to just for that. There may be other reasons before you actually get to run it, even just compiling. But yes, sometimes you have to run it as admin. Now, what was it? EP4CE6, and I can't see. Let's go to the available devices, right? Specified EP4CE6, and then we want E22. CE. I'm sure it's here. I saw it the other day. It's a little far away.
You could put the name in the filter.
Where's the filter? Oh, you're right. Let's do that. Thank you. EP6.
I see there's two versions. There's one without the L, and then there's one with L, with a core voltage of 1.2 volts, and the other one just 1.0 volts.
EP4 CE6 E22 C8. Okay, so it's the non-L version, right? It's the 1.2 volt version that you want. Okay. I don't know why I had so much trouble seeing it that time. When I did it for the screenshots, it popped out to me straight away. It's obviously I'm nervous doing it live. Okay, so that's the device we want. And we could set stuff up here, but I'm not going to. And that's all we're doing. We hit finish and wait for it to set it up. Okay, so there we are. Right, and there's our top level design entity, half adder. And if you double click on that, it should take you to the file where that entity lives. But we haven't added a file, so that file doesn't exist. So now what we need to do is to go File, New, and then select Vhdl file, right? Design files, Vhdl. As I think I said, I'm going to try and do something a little different. So I will go back over this to do it the way the lab is going through. The way the lab says is to select Vhdl file. However, I'm going to try and do it live using the block diagram or the schematic capture approach, which is very, very similar, to what happens with multisim. Okay, so I'm going to use block diagram. So here's the block diagram, and now I need to insert some sort of a symbol. And if you look at the libraries, it's the primitives we're mainly interested in. And I thought I would set up the input pins first. Okay, so we've got an input pin, and that's really tiny. Let me see if I can make it, I wonder if just the standard zoom. No, I don't know where the, what's the standard zoom? Control space. There we go. Let's do that, control space. Right, so there's our first input pin, and I'm going to change the name. I'm going to call it A, right? So if you remember, our inputs are A and B, and now I'm going to insert another input pin, right? And I'm going to try and line that one up, and I'm going to call it B. Okay, and then I'm going to do the outputs. Right, so that was an input. Now I need an output. And I'm going to put that output there. And I'm going to call this one sum. I could call it S. And let's make it a little bit more explicit, called sum. And I'm going to do another output, which is the carry. I don't know if that's exactly lining up, but let's do that. So it's the carry, or C. Okay, now we need to connect them up, and let's remember what we're trying to do. Did I put it here? There we go. Right, remember the sum is the exclusive OR of A and B, and the carry is the AND of A and B. So let's do the sum first, and I'm going to insert another symbol, but this time I need to go back, and it's not a pin, but it's a logic device. And let's have a look. It's not an AND 12, that's a 12 input AND gate. It's an AND 2, which is a 2 input AND gate. Okay, so there's our AND device. And that's going to be the carry, right? And then the other device we need is an exclusive OR. And again, it's going to be in the logic list, and it's probably going to be all the way down the bottom where X is, right? There it is there, exclusive NOR, exclusive OR. So let's go with exclusive OR and the sum. And then what you can do is you can just select there and left click is what I'm doing, and connect up the wires, right? And then left click, drag, and connect up the wires, right? And now I need left click, connect that one, left click, connect that one. I'm just going to move this down a bit to make it a bit easier to read. And I'm actually going to, let's do this. I'm just going to move that down so that it aligns better. I'm going to move that one down so that it aligns better. I'm going to move that one down. I really highly recommend that you move things around so that they look a little better. And then what I can do is I can move this one to here, right? And I can move this one to here. And we're pretty much done. Okay, so there's our, that doesn't look too dissimilar to what we did in multisync, right? In fact, it looks pretty much the same. Let's see if we can save that. And it's already saved it as a half adder because it's assuming that this is our top level entity. So it's renamed it half adder.bdf. So let's do that. We've saved it. And now we should be able to compile it. Once it finishes saving, it's decided to get, there we go, it's saved. Right, and now what I should be able to do is hit this blue play button, start compilation, and let's see what the output tells us. Just thinking about it. Right, and let's have a look at the output of the compiler. Because I haven't done this before, I suspect I'm going to get an error. Right, elaborating entity half adder for the top level hierarchy. Timing driven synthesis is running. There is a warning here. That's what the little yellow triangle is doing. It's saying number of process sources has not been specified. Each may cause overloading on shared machines. Set global assignment in your QSF to appropriate value for best performance. Okay, implemented 6 device resources after synthesis. Final resource count might be different. So it's going pretty well so far. Quartus itself rather than our design. Our design so far is all good.
I had some red error key showing up and I'm not sure why.
Sorry, you have some what?
Like red warning code showing up and I don't know why. There's like...
Okay, can you share a screenshot into the discussion channel on Discord so we can have a look?
Sure.
Okay, we've got another couple of... Oh, that's the same warning. Feature logic clock is only available with a valid subscription license. That's okay, we don't have... Some pins have incomplete I/O assignments. Right? You may have noticed I haven't done any pin assignments at all. So the top level, right? So when you did the project, the new project wizard, you probably didn't name the top level entity as you've named it there. You've called it there half adder without the underscore, right? So it's looking for something called lab 3. If you go to, I think it's up here under file, maybe not. Oh, that's right, it's here. If you go here and you go right click settings, and under general, you will see top level entity, and I bet your top level entity way is called lab 3.
It is.
Right, so just change it to half adder without the underscore like you've named your BDF file, and that should get rid of the error. Okay?
Sounds good. Yep, thank you.
You're welcome. Okay, number of processes, we did that. Another warning is telling me there's no pin assignments. Before we go from compiling and simulation into deploying the design on an actual device, we need to assign pins. And I'm going to go through it now, but I'll go through it when we need it later on. There is this assignments menu option, and the thing we need to look at is called the pin planner. Right, and hopefully that loads up. So here is the pin planner. and there's a picture of our device. And I'm just gonna, I suppose I could make it a bit bigger than that. Right, and our design has shown that there are 2 inputs and 2 outputs, and so our pin planner is saying, hey, here are all the inputs and outputs in your design. I need to know where to route them to the output pins or the input pins, and that means I have to fill in this location column. Okay, so how do I figure that out? Well, you need to go to the GitHub. Can I do that here? Let me just right swipe and then go to the GitHub. So this is the GitHub entry for the full digital logic one, and if we scroll down on this page you will see the pinouts, right? And what we need is, what we want to do with this one is we want to connect up inputs on our design to 2 of the switches, and we want to connect outputs on our design to 2 of the LEDs. Right, so here are the keys, pins 88, 89, 90 and 91, and here are the LEDs, pins 84, 85, 86 and 87. You'll notice that this dial switch and these keys connect to the same pins. By dial switch they mean this dip switch. It shouldn't be dial, it should be dip. Right, so these switches here, the dip switch, override what's happening on the push button. So in general, don't touch these dip switches. Just use the push buttons. This dip switch, when you actually get the board, it's a bit hard to see on this picture, but there is actually a layer of plastic over the top, and it's hard to access these dip switches. Just do what the plastic is telling you and don't touch them. There's a cutout on the plastic that allows you to push these push buttons, so that's okay. Okay, so what did I say? Let me just push this back to a different screen so I can read it at the same time as reading this. Right, so what I do is I'm going to say that key 1, which is pin 88, and the naming is pin underscore 88. Right, that gives me the location, and I'm going to do the other one as pin 89, pin underscore 89, and then my outputs I want to go to LEDs, so I'm going to say pins 84 and 85. Maybe? Oh, it's hanging on me. That's interesting. There we go. So pin 84 and pin 85. Okay, and now if I get out of that, what that should do is that...
I'm sorry.
Yeah, go ahead.
I'm sorry. What was the second pin? I can't really see it.
The second pin for which one?
Yeah. The second one, the B. Ooh.
Oh, okay. So I decided that the A was pin 88 and B was pin 89, right? So key 1 and push button 1, push button 2.
Okay, thank you.
Okay. And then the LEDs I selected were the LED 3 and LED 4. Maybe I should have selected LED 1 and 2 to match 1 and 2 here, but I decided to go with 84 and 85, the lower numbers in both cases. And it's just capital PIN underscore and then the number. Okay, let's see if we can bring Quartus back wherever it got to. There it is. So the reason I say I went there is because I was looking at all the warnings, and I'm just going to just look at the warnings, right? So the reason I did that is because it says some pins have incomplete I/O assignments. Refer to the I/O assignment warnings report for details. This is just warning that there's no clocks. This half adder doesn't need a clock. This is an asynchronous circuit. It doesn't change based on the clock changes. It just changes based on its inputs. And then these are just the previous warnings we had, and these are just the previous clock warning. Okay. Regardless of what technology you're using, whether it's a C compiler or a C# compiler or a Java compiler or a VHDL compiler, read the warnings and understand what they mean. If you don't understand what they mean, find out. Because they usually, in my experience, come back to bite you if you don't understand what they mean. So that's why it's worthwhile reading those warnings. And you can just focus on the warnings by clicking on that little yellow triangle filter in the menu there. Okay. That is pretty much done the whole lab that I want you to do today. I didn't, like I said earlier, I didn't want to do the simulation piece. I didn't want to do the deploy to device piece because you don't have devices yet, and like I said, I want to try and get that sorted out over the next 2 weeks. And just for your interest, if you get a device, I'll aim to meet you somewhere on campus at a mutually agreeable time, and I'll hand over the device. I don't know whether, I think all the devices are still in the trunk of my car at the moment, except the one that is mine. Okay, everybody okay with that? So what I'm going to do now is I'm going to go back and do the lab as it is stated in the lab write-up. Okay, I wanted to do this just to show you that the step from multisim into Quartus is almost direct, right? It's doing exactly the same schematic capture. Looks a little different, but it's pretty similar. And oh look, now that we've assigned those pins, right, the pin names come up in the schematic, which is kind of cool. I hadn't seen that before. That's very cool. Okay, so it's nice that it all hangs together. So what I'm going to do is I'm going to save all of that. I'm going to close the project, and I'm going to do a completely new one. Close project. Right, so I'm going to do another new project wizard.
Where do you find the pin layout?
The pin layout, it's on the GitHub. Let me just post that into the, it should be in the links.
Okay, I was looking on Blackboard, that's why I couldn't find it.
Yeah, sorry. I probably shouldn't use too much. But I just posted it into the discussion. It's on that first page in the link that I posted into the discussion. Okay.
Thank you.
You're welcome. So I'm going to do it again, but I'm going to call it Live 2 Lab. And what is the name of the project? I'm going to call it Lab 3, Lab 03. And again, I'm going to call it the top level design entity half adder. And that doesn't exist, so let's create it. Yes, that's good. I'm going to go with an empty project again. I haven't got a VHDL file yet. Now I need to do the this searching again. And I'm going to, I keep forgetting the number. I really should remember the number, shouldn't I?
It's like the fourth one from the top. It ends with 8.
There we go. Very good. Yeah, I remember seeing it pretty quickly before when I did the screenshots, but I don't know, maybe it was just nerves. Thank you. So we'll select that one. And I don't do anything there, and just go finish. And that should do the right thing. And hopefully that sets it up. And again, we've, as you can see, we've got the top level design instance. Sorry, I'm missing out what's happening on the chat because I think I've got I would like you to submit the VHDL version. Okay, I think you've already shown me that you can do the schematic style by doing multisim. I did want to show that you can do the schematic style using Quartus, but the aim of this course is primarily VHDL, so I do want you to do it using VHDL.
You don't want the entire Quartus project zipped up?
I think that's what I said. Let me just see what I said in the lab.
You say zip the Quartus project, that's why I was just clarifying.
Yeah, so I want to be able to download it and load up the Quartus project into Quartus myself, so I can see it. So I not just the .v project, not just the VHDL. Okay. Okay, so that's that. And as we saw before, because if I double click on that, it should take me to the implementation, but it can't find it because we haven't added a VHDL file. So let's add a new VHDL file this time. Before I did the block diagram, but I'm going to do a VHDL file this time. And I'm going to save it before we do anything. And it's just called it VHD1. Now, how do I change the...
I had to type words into it before I could save it.
Oh, okay. So, well, let me just cut and paste the sample code that I put up on Blackboard, right? So there's the sample code, and then maybe I can save it. There we go. And now it changes the name like it did with the schematic capture version. Okay, so now I tend to be a bit pedantic and I like appropriate spacing. I just cut and paste that directly from the code on Blackboard, and I don't like the spacing that it decided to do there. So I prefer seeing paragraphs of code. It's up to you, but I just find seeing paragraphs of code with appropriate indentation looks a little better. It's a little easier for me to read. Now, I don't know whether I can... Yeah, I can't make the size of that bigger, I don't think. There. So just remember, you can put comments in here. And comments start with 2 minus signs. And it should go, the text should go green if you do that. Okay. And you can also put text comments after a line of code. So right, that doesn't implement the sum correctly. Okay. Right, and if you have a look, let me just see if I can find it here. If you have a look at the rubric, if all you did was just what I did, which was making sure the Vhdl compiles and appropriate naming, then that's worth 60% of the grade. If you actually then implement the half adder, that's worth the extra 40%. Okay, so whenever I try with all of my labs and assignments to post a rubric, so I suggest you get into the habit of reading the rubric before starting any of the submissions. Okay, we've got a problem. It's saying the top level design entity is undefined.
It's probably because you named it
Lab 3. Look at that. So I need to change the name of the entity to half adder. And then there. And then just for naming consistency, I'll change it to half adder arch in the architecture section. Okay, so that's saved, and now let's try another compile. We'll see how that goes. Hopefully we don't get any errors this time around. And again, we've got that one warning, and that's just about how Quartus works. Ooh. We've got some warnings here. That's interesting. Ah, well. I assume that's hardly surprising, right? Because that's all we've done with them. Right? We've just set them to be ground. But it's interesting that Quartus picks up on that and tells you, hey, you've just got grounds here. And then here's another interesting warning saying that we haven't done the right thing. No output dependent on the input pin A and no output dependent on the input pin B. Like I said, read your warnings. They're telling you something. Understand your warnings. If you don't understand them, find out. And again, it's giving me the incomplete assignment because this is a completely new project and I haven't done the pin assignment yet. Let me just see if I can Go in here. I think that's the one. Okay, but we're still compiling, unfortunately. But I think the only thing we need to make sure of is... Yeah, sorry about that. Any idea how to do that?
Yeah, go to Tools.
Yeah.
Options.
Options?
Font.
Ah, there we go. Sorry about that. And let's make it... I don't really care how big it is. Let's see if that works.
It changes all of them, so look a little.
That's odd. It didn't change the ones I wanted to change. Yeah, see, the one I wanted it to change is the one in here. Let's see if there's another option. So Tools, Options, Fonts.
Maybe it's the one in Text Editor.
Where's that, down here? Yeah, that's the one. So let me before we go there, let's just make that a little smaller because that's a little large and we don't really need it. I'll make it bigger than standard, so we'll leave that at 20. And then down here, let's make the fonts for messages at 20 as well, rather than 10. And let's just see if 20 is big enough for the text editor. 10 is too small. I apologize, I should have figured that out beforehand. So there, is that better? That's a little better. Is that big enough? Okay, thank you. Okay. Yes. So my you can see, maybe you can't read the message that came across there. My daughter had just had her haircut today, and we have a tradition in our house that whenever anybody has a haircut, we buy donuts. So my wife's just telling me that donuts are available, which I'll have them after the class. Okay, it's still going. We've got let's see if I can just make this one a bit bigger, see where we are. We're in the timing analysis piece. Right, and we're nearly there, and then we do the net list, and then we finish. So this has taken 6 minutes so far. This is an inordinately long compile. Mostly they don't take this long. I'm not sure whether it's the way this was installed on the Citrix server, or maybe there's lots of people on the Citrix server using up the CPU. All these...
I was going to say, I was able to compile about twice already, and it's finished.
Yeah. So it's probably to do with the Citrix server being a little slow. I have a really old laptop just down there. I don't know whether you can see me. I can't see me. It's down there, and it compiles faster than this. So the only reason the main reason I'm using the Citrix server here is that my desktop machine is an Apple, and unfortunately Quartus isn't available for Apple's natively. I actually tried to run Quartus in a virtual machine on my Mac, and that sort of worked. I could do all the compilation and everything, but when you start deploying through the USB, the virtual machine, that deployment over the USB, the timing needs to be exactly right, and you can't guarantee that with virtual machines. So I could only do a program, even for simple stuff like this half adder, I could only deploy the program to the device about one time in 5. Every other time it'd balk. And that was the other thing. If I do it on my old laptop, it takes like 2 seconds to deploy. It would take up to 12 minutes on the virtual machine on my desktop machine. So, and my desktop machine's like, I don't know, 8 times faster than the laptop that I have. So I don't know what that's about. Okay, we're all done, and it finished in 7 minutes and 40 seconds, which is a little long. What did I want to do? I wanted to attempt to show you how to now start doing a oh, I can't do it. Sorry. I started trying to do this on the Citrix machine during the week, and I realized that they haven't installed Model Sim on the Citrix machine, and I had to put in a request to have that installed on the Citrix machine image. In order to simulate what's happening on the device, we need the package called Model Sim. If you did the downloads, I asked you to do the 3 individual downloads from the Intel site. There was Quartus, there was Model Sim, and there was the device, the Cyclone 4 device support. You do need all 3 of those to be installed in order to do end-to-end compilation, simulation, and deployment. So let me just see about that. Where are we going? There we go. Oh, I don't know whether I uploaded it. That might be the problem. Thought I uploaded it. There it is. So I might have to there it is. And let me just see if I can change the font. Okay, there we go. So let's move that. So as far as today's lab is concerned, I've already done it. I've done it twice, right? I've done it once the schematic way, which I don't want you to do, but I did want to show you how to do it. And I've done it the way I want you to do it using Vhdl. What I haven't shown you is what to write here in order to get the sum, and what to write here and in order to get the carry. And remember, sum is probably something like A and B, and carry is probably something like A XOR B. And that's pretty much all you've got to do. I'm not going to get you to do it today, but I will get you to do it in a later lab, and that is the simulation part. And let me just show you. I think that's all I need to do here. I think I'm just going to... I'll leave this running in case anybody has any other questions. but let's just quickly have a look at this. Right, so when you want to simulate, you need to create a separate Vhdl file, and it's not called a, if you saw before, the half adder is .vhd, and that's because that's just the standard Vhdl. This one here is a test bench, right? So the file name extension for a test bench is VHT for test. It is still a VHDL file, right? So you still have to have an entity and an architecture. The difference is, as you can see here, here's the entity statement. There's no port. There are no inputs to a test bench. There are no outputs from a test bench. Well, there are no logical inputs and outputs. The main thing that you want to describe is the unit under test. And remember, in this particular example, the top level entity I didn't call half adder, I called it lab3. So this here is defining an instance, I1, of a lab3 entity, a half adder entity. And then the next mapping is just between this lab3 component and the components of the inputs and outputs available on this device. I haven't talked about it, and I won't until next time round. There is a way to get multiple things to happen at the same time, and that's via the process statement. When you create this VHT file, this is just, it's auto-generated, right? Once you tell it what the top level test thing is, it'll auto-generate everything except the stuff down the bottom that I'm going to talk about shortly. And so one thing, sometimes you need to do some initialization, and that's what this is saying. This code only executes once, so if you need to do initialization in your test, you do that here. For this test, you don't need to do that initialization. And then the next piece is the actual test, right? And what this does is it sets A and B to both 0, and then it does an assert statement saying S has to be 0. And if that fails, if S is 1 or something else, then it'll report out failed S00, severity error. It'll also check the carry output, and it'll say that. Then it'll wait for 100 nanoseconds and change A to 1 and check that the sum is 1, and if not, fail and check that carry is 0. Then it'll swap A and B's. A will go to 0 and B will go to 1, and it'll again check that the sum is 1 and the carry is 0. Then it'll again wait 100 nanoseconds and set the inputs to both 1, and it'll check that now the sum is 0 and the carry is 1. And then it'll just sit there. And when we simulate, what this is going to do is it's going to give us it's going to test our design, right? And so I'll probably put together a lab for next week to allow you to simulate the design. It'll depend on whether I get them to install Model Sim on the Citrix server by then. So we'll see. I might just move on to the full adder piece. Okay. So that's the test bench part of how to play with Quartus. I think that's all I have. Does anybody have any questions? Can you show what exactly we're putting in a zip? Sure. So let me just, so when you do the zip file, you can't have Quartus running at the same time. Okay, so the first thing, once you're happy that everything's together, and I haven't implemented the half adder here, so this is only going to get me 60%, right? Because I didn't actually implement the half adder. What you do is you go to, now I've got to remember where I put it, and this is on my local machine, so I can probably do it a bit better than this, but let's just go this way. No, that's what I went through with the the rubric. If you don't change anything about the Vhdl but get it to compile, you'll only get 60% for lab 3. If you change the statements for S and C in order to make the sum equal to A exclusive or B, and you change the carry output to be A and B, then that will give you the full marks for lab 3. No, so again, Ray, where I'm not, I want you to implement exactly the half adder using Vhdl. Okay? No worries. So let me, where we got Dropbox, and I think it's Peter, Professional, CCSU, OneDrive, Logic Design, Fall 2020, Labs. So actually, I think I called this one the one where I did the Vhdl version rather than the schematic capture version as Live 3 Lab. Just go there and say, where does it send to? The compressed folder. And just try and do the whole thing there. I'm hoping it's not going to be too big for maybe that's going to be too big. Let's see how big it ends up being. This virtual machine's a little slow. It's probably also because it's doing it from the virtual machine over at CCSU down to my local hard drive here in West Hartford. So that might take a little bit of time as well. If it matters, and let's make it easier, right? For this one, I don't think it matters. So let's not do the zip file. I'll change the suggestion in the lab. What I'd suggest is just going into lab and then just add the VHD file, right? And just submit the VHD file. That should be plenty for me to be able to tell whether you've compiled it. I wish there was a standard way of changing font sizes. It's okay if you submit the zip, but let's just see how big the zip file was. It might be a little large. Oh, it's not too bad. It's only 2.8 megs. So yeah, just do the zip. Let me do this. I'll give you the option. You can either do the zip, or you can upload a screenshot of having compiled the VHD file and the VHD file. Does that make sense? Okay, I think I'm done, unless anybody has any other questions. I killed Quartus there, so remember you won't be able to zip the file unless you're out of Quartus, because it complains about something getting access to the file when it tries to zip it otherwise. Upload the VHD file and a screenshot of the successful compilation of the VHD file, Jacob. Okay. Let me do that right now. I'll edit this lab 3 if I get to it. There we go. So you have the option, either submit the zip file of the whole project, or a screenshot of successful compilation okay. No, the waveforms and everything, you won't be able to do those. Well, if you've already installed ModelSim locally, you'll be able to do them now. But I want everybody to have access to them before we do the waveform simulation, and it's not yet available on the Citrix server. So I'm going to hold off on doing that yet, Kyle. Okay. Okay, so they're the two options. Upload either the Quartus project or a screenshot of successful compilation and the associated VHD file. Okay, thank you everyone. I'm going to stop the recording and go get my donut, I think.